Hello friends, I'm Khushal Sharma, a third year right here at IIT Mandi, and in this video I will try to explain to you, and will try to demonstrate a 2D flow problem across an obstacle. So if you have read about and studied fluid mechanics, then you must know that there are two types of fluid problems basically, and it can be classified into external flows and internal flows. So if you have really studied fluid mechanics, then you must know that internal flows occurs in a pipe. A flow which is surrounded from all sides. That is, it has walls on all sides, right? While external flows occurs in an external environment. That is, it generally have flows in one or two direction only. Okay, so that is the case in external flows. So since we are talking about external flows only, so I won't be going into deep into internal flows. So, what is external flows exactly? And as I explained, external flows have walls on mainly on in two direction only. It isn't surrounded by walls on all directions, right? And we can experience like you can think about the application of external flows like in the case of aerodynamics and aero vehicles like drones or planes, etc. Like a flow of planes or drones through an air or a flow of submarine through water. So those are the case of external flows. So let's start with the problem that is a 2D flow problem across an obstacle. And I will be looking specifically into an elliptical obstacle, and this elliptical obstacle will be kept along the streamline. That is, the major axis of the ellipse. This elliptical obstacle will be along the flow of the problem, right? So let's initially start with the theory of the problem. So what is happening behind the simulation that will be performing over here? So the domain that I have took over here will be 15 units in the horizontal direction, that is along the flow direction, and will be of 10 units in the vertical direction, that is perpendicular to the flow direction. While the elliptical obstacle that I will be using, which has its major axis along the flow direction, will have 2 units in its major as its major axis and of 1 units as its minor axis, right? So yeah, that's basically the description of the domain and the obstacle that I will be performing the simulation upon. So looking into the governing differential equations that will be used over here are the main three fluid equations, which are continuity equation, x momentum equation, and the y momentum equation. I'm sorry for this misalignment in the PPTs, text misalignment. I genuinely apologize for that. So continuity equation. What is, as you might know, continuity equation is one of the basic equation of the fluid flow problem. And x momentum equation and y momentum equation are the are the subparts of the Navier-Stokes equation. So one of the few assumptions that I took over here are is that the flow is incompressible, right? So density will be constant throughout the flow; it won't be changing. So that's why these equations are possible. Otherwise, you might be seeing some variable density terms. That's why, right? That's assuming the fluid flow to be incompressible. We'll be using these three equations. Moving on to the boundary conditions. So there, as usual, right. So there will be no slip boundary condition on all the walls present in this domain, that is top wall, bottom wall, and the elliptical domain, that is elliptical boundary or elliptical obstacle. There will be no slip condition that will be applied over there. Then as I mentioned earlier, the fluid I have considered the fluid to be incompressible. That is, density will remain constant throughout the domain, and this is a 2D transient flow, and there will be a gravity free space. Further, I have took the velocity at the inlet. So where is the inlet? So inlet is this initial wall of the domain, right? The wall that is the vertical wall that is closer, like it's not a wall actually, but physically you can consider, not physically even, but the vertical line that you can see in this domain, right? So this is the part that I mentioned as inlet, and the velocity of the fluid over here will be 1 meter per second. So let's moving on to the simulation setup. I will be creating this geometry using a Gmesh, and then the workflow would be like I will be selecting a solver, and I will be explaining why I'll be selecting that particular solver only. And I will be taking and editing and modifying the tutorial based on my conditions, that is the geometry and the domain, and then we will further view and understand the result in the ParaView software. So moving on to our simulation setup. Let's go to the terminal to begin. Right. Okay. So let's begin with CD. Let's see what directories do we have actually at the desktop, right? So listing all the directories, that is using ls. So as we can see, we are in desktop. Let's create a directory over here. Make directory using make directory and name our folder where we'll be storing all the files of our assignment. That is a problem of our simulation. Make directory. Let's name it L assignment, right? It's easier to understand it this way. L assignment. I'm sorry for the typos. L assignment. Okay. Moving on. Let's change the directory to this L assignment. L assignment. Assignment. All right. Again, sorry for the typos. Assignment. Okay, it's done. Now we have to create a first. What do you guys like? You guys should actually also think that we need a geometry to perform a simulation upon, right? We can't directly go to the solver and set up our physics and do all this stuff. We need a geometry and an obstacle on which we want to work upon, right? So we should start with that only. So let's create a geometry file. Make directory geometry. Okay, let's change the directory to the geometry. Okay, yeah, it's done. Now let's create the geometry file, and the geometry file can be, that is the code that is used to create the geometry file is gmesh, right? I will be using the gmesh software over here, gmesh, and the file name. So what is my file name? I will take hellipse dot geo. All right. Okay, so here we are with the gmesh software. Now let's start doing this. Let's start creating a geometry. And in the under the geometry section, under the elementary entities, tap on the add point, and you can see a lot of things that you can add. So we will first start by drawing our domain, okay? And for that we will need 4 points to describe a domain. Let's say that a first point is 0 comma 0 comma 0, that is origin of the this Cartesian system, right? Let's do this. Okay, as mentioned earlier, in the horizontal direction, our domain size was 15 units, right? So let's do it 15 comma 0 comma 0. Okay, it's done. And now in vertical direction, it's supposed to be 10 units. You can always go back and check out the dimensions that I mentioned for the domain. My bad, sorry. 15, 10, and add. Okay, wait. It's not added, right? I can't see my point. I have to do it again. 10, okay, and okay, yeah, we can see 3 points over here, 0 comma 0, 15 comma 0, and 15 comma 10. Now 1 point is remains 10, 0 and 10. Okay, so now we have 4 points. Let's, oops, I guess I defined the wrong font over here. We can always go back and undo the last thing. Just click on remove last script. This button, that is second last button, the script menu, and the last second button will be removed. All right. Again, at the fourth point, that is 0 comma 10. 0 comma 10. Okay, now we have 4 points. Now we will need the lines to describe this domain, right? Let's start with the lines. The start point is 0, comma 0, end point is 15. Again, start point is 15, end point is 15, comma 10. Again, start point is 15, comma 10, end point is 0, comma 10. Again, start point is 0, comma 10, and end point is 0. Oops, it's not selected. Yeah, it's done. Now, what are we missing over here? We are missing, right? We are missing an obstacle. Again, what do we need to define an obstacle? The points. The points to join and form the arc, right? Let's begin with the points. So let's keep the center of our ellipse at, let's say, 2 comma 5. So this will be the center of our ellipse. Okay, and now let's define the right hand side of our obstacle at 3 comma 5 and the left to be at 1 comma 5. So these 3 points makes up our major axis. Defining our minor axis, 2, and let's keep it and let's keep this again 4.5. Okay, so this vertical line defines the major axis of our obstacle. Okay, now what do we need again to join all these points, right? To define our geometry, to define our obstacle. So we will need an ellipse arc over here. Let's define the start point. Let's keep this at the start point. Sorry, it's difficult to align sometimes. Yeah, then center point and the major axis point. This is major axis point and the end point again. This is, yeah, first curve is present. Again, start point is this major axis point only. Right, center point, center point and major axis point and the end point. Right. So two curves are present. Again, the start point is this, center point is this. Okay, center point is this, major axis point now this time is this one, second one, and the end point is again this one. Third curve is there. Again, the start point is this one, major axis point. Uh, Again, difficulty in aligning. Center point and the major axis point and the end point. Yeah, so we are done with our obstacle. Now, what do we need? We need to define the plane surface, that is the domain surface, right? Through which a fluid will be flowing, plane surface. The surface boundary is this one, and the whole boundary is this one. Press enter, press E. Uh, Press E. It should be done. Yeah, it's done, right? So if at any time you feel that there is an ambiguity and you think that plane surface has not been defined yet, then you can always go back to this edit script option. Yeah, you can see over here that my plane surface has been defined, right? Although I was having difficulty in pressing the E, but yeah, it's defined. That's my keyboard issue actually, but no worries. We can move on. Now, what do we need next? We need to extrude the surface, right? It's, it can be done from here, translate, and yeah, over here you can see now we need to define the surface, select the entities. This is the surface. Now press enter and press E. Again, having the same issue of command key E. Yeah, it's done. Having the same issue and selection. Wait a second. E. Yeah, it's done, right? You can see this. Just making sure that my trans this extruding part is done. I will make check again this code, and yeah, I can see this extrude command is done. Two things to make sure after extruding the surface is that you need to define a command of layers over here with this, my bad, layers 1 and then recombine to combine the surface. Okay, we are done. Now what we need to do is come back over here and reload the script to reflect these things over here. All right, now you can check the mesh. This is the 3D mesh, 2D mesh, and this is the 3D mesh. All right, you can see we have a 3D, 2D surface, right? Now we are done with our geometry. But one thing we are missing over here is that we can see that this is a uniform mesh. But if you have studied the external flows during fluid mechanics, then you must know that there's a kind of a boundary layer separation and the development of boundary layers that is occurring around the region of obstacle, right? There's a lot of what can I say, interactions and instabilities of the flow that's going on around here, right? So in order to get an accurate values of our properties like velocity, pressure, we should have a additional node points around this obstacle, right? So how can we get that? We can get it by the code of this Gmesh. We need to just define this. We need to just define these points, right? The points over here. We need to convert it to 0.1 and we need to convert these points to 0.6 and we'll be done with our unstructured mesh. It's kind of a redundant task, but yeah, once it's done, it's quite enjoyable. 0.1, 0.1 again. And for the first points, we will go with 0.6, 0.6, 0.6, again 0.6. Oops. There is a bracket and then 0.6. All right, we are done. Save the script and we can reload it over here and viewing it 3D. Yeah, you can see. Just a second. Save control. Yeah, you can see that we have a finer mesh over here around the obstacle, right? So let's now move on to defining our surfaces. What are the surfaces that we'll be using? So under the physical groups, yeah, under the physical groups, add and define surface. You can see this option over here. Let's start by defining inlet. Where is our inlet? Wait, I didn't put it. Yeah, we can see it clearly in this way. Let's define the surfaces inlet, right? This is our inlet, this dashed line, right? It's selected and our inlet is done. Press E to end selection. It's done, right? And you can see why it gets blue when you make a selection. Now let's define the outlet. Which is our outlet, this dash line over here, and it's selected. Press E to end the selection. It's done. This gets blued. Let's define the top wall. Top wall is this one, right? It gets selected and we're done. Press E to end selection. Bottom, it's this one. Press E to end selection. Now front back to define the front and the back surface. Front, back. Right, we need to define the surfaces, its front and the back, and press E to end selection. Now ellipse, that is to define the geometry, right? Ellipse, which is ellipse over here? This one. Sorry, my bad. We need to select this dash lines over here. This defines our ellipse. Okay, so our ellipse is done. Press E to end the selection. Okay, now our obstacle is ready. Right, now we to define the volume, right? In the physical groups, click on the volume, select the volume that will be used, click on the center obviously, and press E to end selection. And yeah, it's done. It gets fluid over here. Just to make sure all my surfaces are defined and it's all done. Reload. Yeah, physical surface, inlet, outlet, top, bottom, front, back, ellipse, and ellipse. Right, physical surface, physical volume, it's all done. Now we can go back to our terminal. Okay, we need to first save this file, right? Export. We have already saved. So let's do this ellipse dot. What's the name again? Wait a second. Right. Uh, ellipse dot msh and select the file type to be mesh gmesh msh. Okay. Click OK and take version to ASCII and okay. Yeah, we are good to go. Let's move on to terminal. First close this. Now moving on to the terminal, what we need to do next, right? We need to, let's see first if our geometry is ready. CD dot dot, it helps us. Okay, okay, my bad. So CD, CD geometry, CDL assignment. It's correct, right? Yeah, spelling is correct. Let's list what is present with us. We have geometry, right? It's created. Now, what do we need next? We need the tutorial part, right? The solver that we'll be using to solve our problem. So I would like to explain about the solver that we'll be using over here. So we have OpenFOAM 10. No, not this one. My bad. Open the incorrect folder over here. Okay, let's start from here only. I'm not able to find it over here. I would have preferred to show it from here, but well, yeah. Wait a second. Actually, I'm having a bit difficulty finding it myself. But anyways, it's easy to locate it from terminal, when you once you get used to it. So let's again start with CD. Now CD OPT, that is open from 10. Okay, CD OPT. No such, okay, ls, no such file or directory is found on as CD OPT. But let's see. Okay, all right. We can go for CD OpenFOAM. Can't, can we get this time? Wait a second. Yeah, and it sometimes makes issue, right? We need to make sure that you have OpenFOAM 10 or OpenFOAM. If you get it wrong, then you won't be able to open it. So it's actually CD OPT in my case, but you should make sure in yours as well before trying it out. CD OPT. Okay, I'm having a bit getting a big issue over here. Uh, सार्थक भाई इशू आ गया मैं हक दिया भाई भाई आ ही नहीं रहा सीडी ओपीटी में कुछ
वो तो बना टिक रहा है ना सीडी स्पेस ओपीटी
सीडी स्पेस ओपीटी
सीडी स्पेस स्लैश
हाँ
स्लैश डॉट ओपीटी
ओपीटी
स्लैश
स्लैश
बस एंटर कर दे
अच्छा अब मेरे को वीडियो वापस क्रॉप करना पड़ेगा
वो जल्दी बनाना पड़ेगा तो जल्दी जल्दी करना
so all right, let's go. Let's begin again. So the code was cd slash opt slash, and we are done. And we are inside the OpenFOAM 10 folder. Let's see what files we have over here. So we have OpenFOAM 10 and the other ones, but we need to go with OpenFOAM 10, right? So CD, OpenFOAM, OpenFOAM 10. Okay. Again, checking the folders which we have over here. So we have applications, bin, build stem, and many more, but we will go with the tutorials one. So CD tutorials. Looking in what tutorials we have, take ls, listing it all out. So we have a lot of tutorials that we can solve. Like we can solve a lot of like problems with OpenFOAM. It's a very versatile one. But the one we will be needing over here is incompressible since our density is constant throughout the flow. So taking CD incompressible. Okay, CD incompressible, right? Now again checking which folders and files do we have under this. So there are various solvers again, solvers again, sub solvers within this incompressible folder. But the one we will be using is CD icofoam. Icofoam. Just checking once the spelling. Yeah, it is CD icofoam. Now you guys might be wondering why are we using the CD icofoam only? That is icofoam solver and not using any other ones. So it is so because icofoam is kind of is a simpler solver. It's used for educational purposes mainly, and for a laminar flow and easy obstacles, easy geometries only. But if there is some industrial grade obstacle, or if the flow is turbulent, let's say, then we can't use this alcofoam solver. We need to go for some complex solvers or some advanced solvers like pimple foam or simple foam, etc. So since we have a simple 2D flow problem across a elliptical obstacle, so we'll go from with the icofoam. Now checking the folders that we have within over here, it is cavities and elbow. Going within the cavity, CD cavity. All right, now we need to copy this folder, that is the cavity part, to our actual problem assignment, like problem folder, right? The assignment folder that which we made earlier. All right. So copying it to there. So the code which we'll be using for this is CPR and cavity and the path which we'll be using, right? So you can always get the path from, wait a second, we don't have it over here. Let's see, do we have it? No. Yeah, actually we do have CD cavity, Mandi, home, and wait, home and Mandi. It's in that way. Home, Mandi, and the assignment name, that is L assignment. L underscore assignment. See, okay, I've not put the correct file name again. CDR cavity desktop. You know what? We can always get the file path from over here also, right? So where is this L assignment, right? This is home L assignment. Just copy the path. Okay. Yeah, just remember it if you can't copy it from here. CD cavity, right? File path is home and L assignment.